The purpose of this lab was to observe the motion of rolling a tennis ball, in my case, at constant speed using a tracker and comparing it to a computational model that we created using a code that we were given in Python. The main question of this lab was to see if the predicted model would be similar to the actual model using the physics principle of Newton's second law. Newton's second law tells us that the net force is equal to the mass times acceleration. And another equation that's really important in this experiment was that the final velocity is equal to the initial velocity plus F net over m times delta t. And in this case, for a constant velocity, the net force will be 0. So the final velocity will be equivalent to the initial velocity. You'll see that in the computational model, it was assumed that it was a constant velocity, whereas in an observed model, that might not be the case. But in the constant model, the final velocity was, in the computational model, the final velocity was equivalent to the initial velocity, whereas that might not be in the case in the observed model. So the way that I divided this up was by looking at the observed model separately and the computational model separately. So in terms of the observed model, the method of measurements that we had to use was that we first had to get the specific measurements and mass of the tennis ball. The mass was 0.05 kilograms and the diameter was 0.67, and we needed to get the correct frames of the ball to minimize the amount of forces acting on it that was used in the video. Additionally, we also used a calibration stick to find the distance that the ball traveled and the diameter of the ball to calibrate the distance traveled. This shows a screenshot in the middle of when my ball was basically moving, and you can see that the tracker technology is able to pinpoint a specific point of mass on the ball and then following it through specific frames to get the specific time and position of the ball during that time. And then based off of that, it creates a graph of the movement of the ball during that time period. So this doesn't encapsulate the full time period that I used. I used about 0.7 seconds. But in the middle of my ball moving, this is basically what the tracker technology looks like. And you have to put in the mass of the ball as well because it takes that into account. And then based off this, I used specific frames to get the ideal situation during which my ball had the least amount of forces acting on it. So after I got this and after I got this data, I put it in an Excel document and so I could compare it back to the computational model results later. And then I did the computational model I used the initial Python code that we were given, but we did have to make some changes to it in order to get the desired output. So I had to change the initial mass of the ball because that was different, the initial position and the initial velocity, which I got from the tracker technology. I also changed the time that was given in the Python code because I used a different time step. And I also changed the velocity and position formulas to update them using the Fnet over the mass of the ball plus the time step. And then for the position formula, I did the same thing as well. I used the position of the ball plus the velocity of the ball times delta t. And then I also uncommented the print statement at the bottom of the code so that I could get the time and the position associated with that time as well. So this was basically the graphic output that I got, and we can see that the line is extremely straight for the position versus time. And then I also got an output of all the times here. And once I did, I pasted that in an Excel document as well. So here you can see are the time and position for my observed model that I used initially using the tracker technology, and then here are the times and positions for the computed model. And then I used those to put it onto a graph, and you can see that the computed model graph is extremely straight because it was not taking into account external forces, whereas the observed model did take that into account because we were doing it live. And then you can see that it's a little bit different than the computed model's graph because it wavers off at the end, which means that it got a little bit slower due to these external forces, which makes a lot of sense. And so that was basically one of my main conclusions. And then if the axes were switched, the graph would basically look the same, but it would be going in the negative x direction rather than the positive x direction and would instead have a downward slope. But the rate at which it was decreasing would be the same at the rate at which it was increasing originally. So only the direction would really change. And we aren't really able to account for every single push and pull that is put onto this graph, but because there are too many individual forces acting on the object to account for them all, so we can only determine the net force rather than the individual forces.